Okay, today we are going to study some non-destructive testing processes of castings. I'm Ghosh, and I'm going to demonstrate to you ultrasonic testing. Alright, now the question may arise, what are the different types of non-destructive processes, right? Now, some of the different types of non-destructive processes are mechanical methods, radioactive methods, magnetic methods, electrical methods, and so on. But right now we are just concerned with the ultrasonic testing. Now, ultrasonic non-destructive testing, which is also known as NDT or simply UT, is a method of characterizing the thickness or internal structure of a test piece, which in our case is a cast, through the use of high frequency sound waves. Now, the frequency which is employed in ultrasonic testing is usually between 500 kilohertz to 20 megahertz. And as we know, the human range of hearing is between 20 hertz to 20 kilohertz, and therefore the frequencies which are employed in ultrasonic testing is much above the human range of hearing. Okay, we move on to the next slide. Now the question is, how does it work? Which is the all important question. Now the thing is, suppose we have this thing in gray, right? Let's call this the workpiece, and this, let's call this a transducer. Now what the transducer does is that it emits signals and it receives signals, and the free end, the other end of the gray workpiece that you see is called the free end, and sound waves are usually reflected from the free end. That is the property of sound waves, right? Now suppose there are no defects in the entire workpiece. There are no defects. In the first figure we see that there are two arrows, one going to the free end of the workpiece and one which is coming back to the transducer. Now that is exactly what is going to happen if there are no defects. But suppose there are defects in the workpiece, then what is going to happen? If there are defects in the workpiece, the defect is going to reflect a part of the sound wave that is sent by the transducer. And since the defect is going to reflect a part of the sound wave that is sent by the transducer, the transducer is going to receive a part of the sound wave much sooner than it should have, right? Now suppose we move further to the right, where the entire sound wave is received by the is reflected by the defect. In that case, it is no part of the sound wave is going to travel to the free end of the workpiece at all. The entire sound wave is going to be reflected by the defect, and therefore the transducer is going to receive it much sooner, the entire sound wave much sooner. Now what we do is we plug this thing onto a computer, and we see it on a screen. Now what we see on a screen is that when there are no defects, there are two the intensity is firstly plotted on the y-axis, and the time on the x-axis. Now when there are no defects, you see two signals. One, the echo signal, which is on the right, and the other one is the receiving signal. Now the other one is the transmission signal, sorry. But when there is a defect, suppose, and a part of the defect reflects the sound, reflects a part of the sound wave but not the entire sound wave, you're going to see three signals, obviously, which I just mentioned before this. But of course, again, if the total sound wave is reflected by the defect, you're just going to see two signals again, but that is not going to be the echo signal from the free end of the workpiece. It is just going to be the signal which is reflected by the defect. Okay, now we also, one more thing that we should mention here is that there is also another there are two types of there are two methods of receiving ultrasound waveform, right? One is the reflection method and one is the attenuation method. Now what we just studied is the reflection method. In the other method, what happens is a transmitter sends ultrasonic through one surface, and a separate receiver detects the amount that has received it on another surface after traveling through the medium. Now the advantage of this method is that imperfections or other conditions in the space between the transmitter and the receiver reduce the amount of sound transmitted, thus revealing their presence, right? So if there are any imperfections in the workpiece, then it is going to be detected through this method. Okay, now we move on to the advantages of this method. The advantages of this method are very simple. Firstly, it is obviously non-destructive because we are studying non-destructive processes. Secondly, access to only one side is required, right? Unlike measurement with mechanical tools where access to two sides are required, like calipers and micrometers. And the third advantages of this method is that there are hardly any health hazards associated with it. There is no potential health hazard that is associated with this method. Okay, we move on to the limitations of this method. Firstly, it will require a trained operator who can handle the computer, who can handle the screen, who can take measurements properly. It will require a trained operator with the necessary experience who can interpret the results. Secondly, the ultrasonic thickness gauges must be calibrated with respect to the material being measured, and applications requiring a wide range of thickness measurement or measurement of acoustically diverse materials may require multiple setups. That is a problem. And thirdly, ultrasonic thickness gauges are more expensive than mechanical measurement devices. So that is the third limitation of this method, that the cost in this method is slightly higher than the cost in some other methods. Okay, with this we come to the end of our slideshow, and thank you very much.